Good evening and welcome back to AP Stats Notes Online. We've been talking about sampling distributions and we want to continue talking about that. The last set of notes talked just a little bit about unbiased estimators, variability in sampling distribution, and wanted to throw in there that very often we want to take a look at shape of our sampling distribution as well. Anytime we create a distribution, we want to go through those things, our SOCs, right? Shape, center, and spread. Shape will help us, you'll see in a minute, will help us do a lot of calculations. Center is where we determine how much bias is involved. Is the center of our sampling distribution pretty close or equal to the parameter that we're trying to estimate or that we're trying to emulate? Depends on if we know the parameter or not. Spread will talk to us a little bit about how much variability there is in a given statistic. Remember, a statistic can be anything. It can be a mean, it can be a proportion, it can be a Q1, it can be 5/4 times the maximum of your sample data. We can create any statistic that we want. Now there are a couple that we're going to talk about specifically, but so if I want to know if that particular statistic is an unbiased estimator and how much variability there is in that statistic, I would create a sampling distribution and see where the center of that sampling distribution is versus what that same calculation on the population is. And then take a look at the sampling distribution and see how much spread there is in there, okay? What we know is that there are some statistics already that are unbiased estimators. We will talk about two of them primarily throughout the rest of this course. They are proportions and means. Those are two statistics that we know are unbiased estimators and produce very small variabilities, depending on some things, and we'll talk about that in a minute as well. The first unbiased estimator that we'll take a look at in these notes is the proportion, or sample proportions. If we take a sample and calculate the proportion of something, then that statistic will be an unbiased estimator. Should be pretty close to what the population proportion is of that same measurement. To take a look at this and to take a look at what happens when we start looking at sample proportions, there's an applet out there called a Reese's Pieces applet, and it's in a collection of applets that is on this website, rossmanchance.com. Someone has collected a bunch of different animations to help explain a lot of different mathematical concepts, and the bulk of them are statistical in nature. So a pretty good resource to go and look at something if you need a little bit more clarification on it. It's rossmanchance.com. You go through, and here there is this applet that contains an animation that has a population of Reese's Pieces with a given proportion of orange candies, and so we'll do this based on orange candies. And so we'll take from the population, take a sample, and then start creating a sampling distribution of the proportion of orange candies in that sample. Now, let's say that there are 45% of orange candies in our population. So this candy machine is our population. If we have the applet take a sample, there it goes. So it's spitting out 25 candies and separating them out into orange, brown, and yellow. Okay? So what just happened? From our population, which is the candy machine, we created one sample of 25 candies and split them up into orange and not orange. And so this is our distribution of sample data right here. And then once we calculated the proportion, there were 10 candies out of 25, so that's 40%. Let's see, the dot plot is actually looking at number of successes, so let's change that over and do proportion of orange candies. Okay? Now, so the first question in your notes is describe the difference in the context of the candy machine, the difference between the distribution of the population, the distribution of the sample, and the sampling distribution of the sample proportion. And so we can fill that in as soon as everything gets up and running here. Okay, so the distribution of the population is represented by the candy machine. That has all the candy in it. Okay, the distribution of a sample is in that in those bins underneath, right down here, right? Right. So this is in the bins under the machine. And then your sampling distribution is the dot plot below that, right? Okay, so there we go. 25 candies, there's one sample. Now, if we wanted to create a sampling distribution, we have to draw more samples, right? So, and to save time, there's another sample created, right? Here's the population distribution in here. Here's the distribution of sample data right here, and the sampling distribution is this dot plot here. Now I'm going to stop animating and create 8 more samples for a total of 10. Okay, there's 10. There's a sampling distribution of 10 samples. So we could go through our process and describe. Okay, and I'll have to recapture here in just a second. But with n equal 25, and we've got 10 samples, we can do shape, center, and spread. Right, the shape. Do you call that symmetric, single-peaked? The center, where's the center? Well, we can actually help out here by having summary statistics created. Okay, and so there we have our summary statistics. Let's actually capture that and take a look at what we're doing here. So again, n is 25 with 10 samples. Shape, center, spread. Shape is symmetric, single-peaked. The center is at 0.44. And the spread in terms of standard deviation is 0.091. Okay? Now, take a look. Shape is nice. Symmetric, single-peaked, almost could be normal, which is good for us. We like normal distributions. The center is 0.44. Well, look at the center versus what the actual population proportion is. It's 0.45 of orange candies. The spread is 0.091. So we'll take a look at that more in just a second. But this is what we would expect our center to be. It should be pretty close to the population parameter because, like I said, proportions is an unbiased estimator. Okay? Now, what if we took more? Let's say we take a total of 400 samples. Okay? Now what happened? Okay? With our 400 samples, we can do, again, shape, center, spread. Now, you're not going to see the sampling distribution here, but we'll go back and forth, right? So what happened when we took more samples? So now n is 25 candies. And now we've got 400 samples. What was the shape? Well, if you look, still symmetric, single-peaked, fairly symmetric. You know, I don't know if you really want to call that skewed right or not, but that's fairly symmetric. Okay? Not perfect, but no distribution ever is. And single-peaked, as a matter of fact, pretty close to normal. The center is 0.453. Again, really close to the population proportion because it's an unbiased estimator. Now look at the spread. Surely with more samples we have more information and the spread's going to be different. Well, it's actually not, 0.092. So apparently the number of samples that we take doesn't have an effect on the sampling distribution. The shape, center, and spread are all pretty close to the same. So number of samples doesn't seem to matter. So let's take a look at if we start changing some things. Okay? What if instead of 25 candies, we take a sample of 50? Let's reset this and take 400 samples. Here, we can do 10 first. Okay? Take 10. Look at the shape. Ooh, don't really get much shape out of this, right? Look at the center, 0.446, still an unbiased estimator. Look at the spread, 0.068. Now our spread, when we had 25 candies, was 0.09. The standard deviation has dropped to 0.068. The spread has gotten smaller. There's where your more information comes from. It's in the number of candies, not the number of samples. You could take 400 samples of the same size and you're going to get the same amount of information every time. If we increase the number of candies in our sample, that changes the game a little bit, right? And now if we do a total of 400, now look at the shape. Shape is normal. The mean, 0.445, is the same as the population, still an unbiased estimator. Look at the standard deviation, still about 0.06, 0.07, which is where it was when we took 10 samples. So again, the standard deviation has been affected by the number in the sample, not the number of samples. There's an interesting distinction to be made there, right? Well, how are we going to change the center? So we know how to change the shape. The shape was weird because when we had 10 samples, we got no shape. And when we increased the number of samples, we started to get a little bit more shape. And that makes a little bit of sense. Okay? So you increase the number of samples to get a clearer idea of the shape of the sampling distribution. But to reduce the variability, we had to increase our sample size, which from the notes over the weekend should make sense. If we want less variability, we simply take a larger sample. A larger sample gives us more information. But our center didn't change. How do we affect change in our center? Well, again, P is an unbiased estimator. So in order to do that, we're going to have to change our parameter, right? So if now we say that there are 15% orange candies, and we take 400 samples of size 50, right? Now look, still fairly normal shape. The center has now changed to 0.15, okay? Because it's an unbiased estimator. Our spread is 0.05, okay? So it's a little bit different as well. So our spread must be affected by the population parameter as well, because the spread's not 0.07 anymore or 0.09, which is what it was in our previous two examples. Okay, now you can play around. Again, go to rossmanchance.com, pull up the Reese's Pieces applet, and play around with this and see how you can affect change in your mean and standard deviation. Okay? So let's go back to our notes and try to use this to to answer some more questions, right? Where are we at? There we go. Okay? Based on the candy machine activity, describe what we know about shape, center, and spread of the sampling distribution. Well, hopefully what you just saw there is that the shape is going to be fairly normal sometimes. Right? Remember that when we pulled 10 samples and we increased our sample size to 50, it wasn't normal. Okay? But it was normal when we pulled more samples. So the shape isn't always normal. We have to try and take a look and find out when it is going to be normal. The center always seemed to be equal to P, the population parameter. okay? And the spread in terms of standard deviation seem to depend on sample size and the population parameter, okay? And so the last question here from the activity, based on the candy machine, when is it okay to say that the distribution of p hat is approximately normal? Now, to show that, I want to, we want to take a look at the applet again. So I suggested that maybe it was the number of samples that helped make this thing normal. Let's try a couple of things here. Let's go take 10 samples of 10 candies where the probability of an orange, where the population parameter of orange candies is 15%. Okay? Let's do that and see what happens. Let's reset this. Take 10 samples. Okay? Not a lot of samples to maybe pull out shape here, although you can get some semblance of a shape. It's like it's going to be skewed right. So let's fix that. I suggested maybe the number of samples will help clear that up. Now it will become more normal, right? Well, look at this. Even with 400 total samples, this sampling distribution is still not looking quite as normal as the others did. Now, the mean of the distribution, of the sampling distribution, is still pretty close to 0.15 because it's an unbiased estimator. The standard deviation is not where they were. It's not at 0.07, 0.09, or 0.05. It's changed a little bit, and so has the shape. Again, sample size affects the standard deviation as well, and apparently so does, the shape is also affected by it. Okay, so 10 candies, not quite normal. What if we took a sample of 20 candies? Is that going to do it? We're getting closer to normal, but we still have a bit of a tail here, of a skewness here. What if we go as much as 30? Closer, we're getting closer. We can go 40, closer still. And if we go back to 50, okay, and you noticed that tail before, okay, it's still not quite normal. There's a little bit of a tail there. So how far do we have to go to get a lot closer to normal? You see it kind of keep pulling in. Keep pulling in. Okay, more and more. Okay, and we keep getting closer and closer to normal. And so that suggests that the shape of the distribution is subject to the sample size. As a matter of fact, if we did the same process but used the 0.45 that we did before, you're going to notice something. Okay, not quite normal, getting closer, right? We're getting closer to normal a lot sooner. And so the shape is also affected by the population parameter, the population proportion. Now, how does all this stuff pull together? Okay, and that's what we want to get to now. So, getting back to the notes here. Okay, based on the candy machine activity, when is it okay to say that the distribution, sampling distribution of p hat is normal? Well, it depends. And what that depends on is sample size and the population proportion, P. Okay? How does it depend on that? Well, based on some trial and error, we've come up with some pretty good rules of thumb. And that's what we get to down here. Your sampling distribution of a sample proportion. The mean of that sampling distribution, the mean on p hat, written another way, and this is going to be kind of weird, the mean on p hat was always equal to the population proportion, always, no matter what we were messing around with. You go back to that applet and you keep playing around with some things, and you're always going to find that the mean of that sampling distribution is always equal to the population parameter, okay? The standard deviation, which in notation is sigma sub p hat, and so we're starting to combine some parameter and statistic notation, so hopefully that's not too confusing. But this is how we notate the mean standard deviation of a sampling distribution. I told you depended on, seemed to depend on n and p, the sample size and the population parameter. And the way that it does is to find the standard deviation of the sampling distribution of p hat, we square root taking the p, the parameter, times 1 minus p all over the sample size n, and that denominator is inside the radical as well. Now, there's a section in the book, page 436, that walks you through where that formula comes from. It's pretty interesting. It has a lot to do with the fact that we're counting the number of orange candies. If we go back to the applet here, we're counting the number of orange candies. You can kind of think about this as taking a sample and counting the number of successes, okay? Because when you pull out a candy, it's either going to be orange or it's not. Okay, the success rate or the chances of it being orange doesn't change every time you pull out a piece of candy, not enough to where it matters, right? We know how many candies we're going to pull out. The way that the applet's sitting right now, we know we're going to pull out 40 candies. So the sample size is set. This all should start to sound kind of familiar. Well, taking a sample and calculating the proportion of successes is a bit of a binomial variable situation. And so this formula comes from the idea of that binomial, where you have successes and failures. And so P could be looked at as your success rate, which is also your population proportion, where 1 minus P then would have to be your failure rate, okay? And of course, n is the sample size. Your normal condition. When is your sampling distribution going to be normal? We mentioned again, going through the applet, that it seems to be dependent upon your sample size, and it took a smaller sample size to become normal, for the sampling distribution to become normal, if our rate of success or if our population proportion was larger. And that becomes what we call the normal condition. The sampling distribution will be normal if is normal if. And what you might have noticed, or maybe you didn't, I don't know, it's kind of, it's not exactly obvious when we go through this. If n times p is greater or equal to 10, and if n times 1 minus p is greater or equal to 10, okay? And again, that seems to kind of come from some trial and error, right? Where this 10 number comes from. It's just sort of an accepted threshold for where your sampling distribution becomes a normal distribution. And again, we like normal curves, normal distributions, because there are a lot of things that become very predictable in a normal curve, right? So your sampling distribution becomes normal. So this collection of samples could fit into a normal curve, at which point we can just sketch the density curve, the normal curve, and use our normal calculations to talk about the proportion of samples that are bigger than, less than, or in some interval of proportions, okay? And this is all true for our sample proportions in our sampling distribution, okay? Now, again, because this is all sort of based on this binomial variable, and again, page 436 does a much better job of going through the details there. That means that the success rate has to be the same every time we pull out a piece of candy. And I mentioned before that it is. Well, we know that's not exactly true. We're not sampling with replacement. We're not pulling the candy out and putting it back in. We're just pulling out 25 or 10 or 40 candies. And so we do know that the probability of getting an orange candy the second time does change a little bit, but not enough to matter until what? Right? All of this is true as long as that probability stays the same or pretty close. So as long as we sample less than 10% of the population, also known as the 10% rule. Okay? 10 shows up a bit. Sample less than 10% of the population, and if our number of successes and our number of failures are both bigger than 10, then all of this stuff holds true. The sampling distribution is normal. It has that mean, and we can calculate our standard deviation using this formula. Okay? Now, that's not what I want. Sorry, hang in there. Okay? The superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a four-year college or university. What is the probability that an SRS of size 125 will give a result within 7 percentage points of the true value? Okay? What is the probability that an SRS of size 125 will give a result? So I want to talk about taking a sample of 125 that give us a result within 7 percentage points of the true value. Okay? Well, what kind of things do we know now? Okay? Well, we know that the population proportion P, or the proportion of middle school students that are planning to attend a four-year college or university is 80%. Okay? If I want to find the probability of a sample giving me a certain value, then I need to understand what the sampling distribution would look like under these conditions. Okay? Well, I know that when I create a sampling distribution, the center of this thing is going to be equal to the population parameter. So the mean of my sampling distribution is going to be 0.8. The standard deviation of my sampling distribution, okay, is going to be equal to the square root of p times 1 minus p all over n, as long as we sample less than 10% of the population. Now we're sampling 125 students. Okay, this is a large school district. We're a large school district. Okay, is it reasonable to assume that there are more than 1,250 students in the population? Is that a reasonable assumption? Okay, well, I think so. You think about 1,250 students out of what, 6, 7, and 8 grades? That's 3 grades. Think about us. We have East and West, right? That's 3 grades. That's about 410, 15, whatever students per grade. And you split that in between 2 schools, and I think we're pretty close there. I think we're pretty okay to assume that. So then we can go ahead and do this calculation. So we take 0.8 times 0.2 and divide it by 125. Okay? So we do that. We square root 0.8 times 0.2 divided by 125. and the standard deviation is going to be 0.036, unless my math is wrong. Okay? Now, so we know the center and we know the spread. Is this going to be a normal distribution? Well, what we have to make sure of, the number of successes. And the way we find the number of successes is we take our sample size. So how many successes would we expect out of a sample of 125? Well, it would be our 125 times the success rate, which is 0.8, right? 125 times 0.8 gets you 100. That's bigger than or equal to 10 for sure. You got to check the failures too. Make sure that we have more failures. We would expect more failures than 10. Well, out of a sample of 125, if we expect 100 successes, then we could probably expect 25 failures, and that's also bigger than 10. That's that normal condition, which means that now our sampling distribution of p hats is going to be normal with a mean of 0.8 and a standard deviation of 0.036, right? And this is not a very good curve, and it's not centered very well. But anyway, we get 0.836 here. We get 0.972 here, I think. Okay, and then we subtract here. So this is always hard for me, 764 and 0.73, I think 28. And check my math there, but I think that's right. Now, we want to be within 7 percentage points of the true value. The true value is 0.8. Within 7 percentage points, okay, means 7% this way, 7% this way. Okay? So within 7 percentage points would be 87%, so 0.87 ends up somewhere right in here, and then 0.73, which ends up somewhere right in here. And so this is the area that we want to find. Now after all of this, now we're back into our normal calculation stuff. So the probability that a sample will give us a p hat that's in between 0.73 and 0.87 is where you go and find your normal CDF and do that calculation. And again, I'll show you that, but I mean, at this point, we should understand we're in our distribution menu, right? Second distribution, normal CDF. Oh, what happened to my mode? No, everything looks like it's good. Here we go. So we go 0.73 to 0.87. The mean is 0.8 and the standard deviation is 0.0. Oh, gotta check it. 0.036. Paste that in there, hit enter, and so the probability of us taking a sample of size 125 and the proportion of middle school students in that sample that are planning on going to school being within 7% of 80%, that's all very, very tough to say. So let's try to write this out. So this is 0.948. So we would say 95%, let's see, there is a 95% chance that a sample of size 125, and it has to be specific to 125, that sample size changes and our calculations change, will produce between 73% and 87% of students who are planning on attending college. Okay, it gets kind of wordy, but that's what that means. Okay, there's about a 95% chance that we'll take a sample, and the proportion of students that are planning on attending college will be somewhere between 73 and 87%. Okay, so that's how we're going to set up our sampling distributions for our sample proportions, and how we're going to do some calculations. As long as this thing is normal, we've got to check some conditions to make sure that we're okay doing that. Okay, so we'll end there. We'll get to some homework and start approaching some different questions within that. Okay, have a good night. We'll see you guys tomorrow.